This is the week 3 answer key. So the first question is just going to be doing this mechanism, and I did this in discussion. But one, if you don't know how to do a mechanism, and let's just say, I know we like teach the mechanism, so a lot of you gotta memorize them. But if you literally have no idea how to do the mechanism, the first step I would do is I try to number carbons or atoms. So if you have a nitrogen or a oxygen that's in it, you can number those too. They don't all have to be carbons, but they can be all carbons. 2 would be find the differences. 3 is going to be find conditions. This is it acidic? Is it basic? Oh, this red pen's running out of ink, so let me switch to this black one. Or is it neutral? And then 4, I try to find my mechanistic arrows, which in discussion I said, try something crazy. And I do that by trying to pretend like it's concerted, or one step. And then finally, you back it out stepwise. So I don't really have to number the carbons to see the differences in this, because in this one, I have a hydrogen here, and basically the differences are that this hydrogen moves, right? I'm in acidic conditions, so I'm in sulfuric acid, and if I had to do this stepwise, or not stepwise, concerted, these are the arrows that you would have to move, right? All these arrows will show up. So now if I just redraw my structure, just redraw my starting material, and I'm here, right? The first thing I'm going to want to do, because I'm in acidic conditions, and especially because I have a strong acid, is I want to protonate something. I'm in acidic conditions. If you're in acidic conditions, you should only have positive charges and neutral structures. So the first thing I'm going to do is create something with a positive charge, and I do that by protonating something. Right? Then I can draw my resonance structure. Then, finally, I can come and take this proton, like that. And that's the mechanism for this. All right, in base, since I'm in base here, remember that the potassium just falls off as K+. So I'm going to take this proton for step 1. Then I'm going to draw the first resonance structure. Second. Oh, my other advice for mechanisms is make sure your mechanism is actually working towards the product you're trying to make. Right? So that's one thing that helps with kind of doing a little bit of a mapping out where things are going to go at the beginning. And here we're going to get all the way to our final product there. So those are the 2 mechanisms. All right, now let's do these Diels-Alder reactions. So remember the arrows in Diels-Alder. It doesn't matter which way around the circle you go, but they go around the circle. And you're going to make your cyclohexene ring. I don't think that the dash is that big of a deal, whether these are both dashed or just straight lines. Don't draw them wedged though. That's one rule, is don't draw them wedged. But Davis doesn't seem to be being picky about that, so I'm just going to leave that there. This doesn't technically ask you to draw the arrows, so I'm not going to draw them all the time. This is an alkyne, so you need to have a double bond still there because we're only using one of them. Right? So that's going to be a structure there. All right, for this last one, this is in the S-trans. So the way I like to do this is I change it to the S-cis, and then this one is only one substituent, which is going to be here, so you can't mess up that top one. On the bottom one, this is a trans-alkene, so I want this to still be trans. Right? Now this, of course, has a resonance. Right? So we got resonance up to there. This also is going to have resonance. I won't draw the arrows because I need to expand the CN. But basically the CN triple bond is going to move like that. You want to match up this partial negative and the partial positive charge. So the correct way to align this is with these pointing towards each other. Right? Like this. So there's a partial negative and a partial positive charge. And these react together, of course, to form this. Remember, this is like going to be a dash CN just because of the orbital overlap that you have with the dienes and the dienophile coming underneath. Right? This p orbital stabilizing those bonds. That's why it's always going to be dashed. I know I drew it on the bottom, so on the top, but it'll be true there. And this you're actually going to get a plus and an enantiomer as well. Right? Where basically you just flip both of these like you flip both of these like a pancake, and then you'll also have it where the OME is coming down, the CN's coming down. All right, last two. This one you're going to get two different. Let's see, you're going to get this and CN this way, but you could also flip this molecule like a pancake. So you should also get, remember the endo rule is making the CN go dashed. So you should also get this. But if you flip this like a pancake, it's going to just be the enantiomer at that. So however you do it is, I don't really care. This is stuck in the S-trans. So this is no reaction. All right, this is retro Diels-Alder. When you do a retro Diels-Alder, you are going to look for the cyclohexane ring. And this is going to be part of your diene. So if I did this, I would draw these four are the diene. These two are the dienophile. So there's my dienophile. Here's my diene. I know it's not set up the way you want it to be set up, but I'm just taking it apart from the way it's presented to me there. And this one, we're gonna get that for the diene. And these just have to be trans to each other, right? Because they're trans here. Now you might ask yourself, well, why is this wedge and that one's dashed? Remember, you can flip this molecule like a pancake and it will look different, right? And it'll be okay. So there, we got those. Oops. I tried to take. All right, we're gonna order these in order of reactivity. So for dienes, remember, these are electron donating groups, and you want electron donating groups on your diene. This is an electron withdrawing group via resonance, right? These take electron density off, so you get a partial positive charge here. This is given a partial negative charge, right? And this is happening by donating electron density via resonance, right? So that's why this is electron withdrawing, this is electron donating. So these we already know. These groups, methyl groups, are also electron donating, and you can figure that out just by knowing that for a carbocation, secondary is more stable than primary. So that means that the extra methyl group is donating electron density to stabilize the carbocation. So this has 2 electron donating groups on it, so 3 is going to be greater than 1, which is going to be greater than 2. For this one, you want electron withdrawing groups for the dienophile, so 4 is going to be greater than 6, which is greater than 5. This, because it has resonance, I think it's a better donator than both the methyl groups combined. Although I don't have experimental evidence at the tip of my fingers to prove that. I believe it to be the case, though. So the best diene is going to be this one. And remember how in the last one we saw that when you have these asymmetrical dienophiles, you want to have the electron withdrawing group and the electron donating group pointing in the same direction, so that you can, when you have this here, so that this partial positive charge and this partial negative charge line up together. Then we can get this, right? So we're going to get that. Now the worst one is, or the worst is 2, so that's going to be this. And the worst dienophile is going to be 5. Like that, right? So this is a partial negative charge and this is a partial positive charge. So they're like opposite of what you want. So when you make this, you're gonna get this like that, right? You could also flip these like a pancake, so there should be an enantiomer. You can flip both of those like in a pancake, so you should get an enantiomer for this. Enantiomer for both. So that's that. All right, this last one we have to do retrosynthesis. Again, I'm gonna not do the whole diene, just because there's 2 different ways you could break this apart, right, to do retrosynthesis. Because there's 2 different cyclohexenes you could have, right? So the star side, let's do the star, and this is the dot side, right? The star side is going to look like this. The dot side is going to look like this. Remember, I'm just doing retrosynthesis here. So let's do the star side first. You're going to have a methyl group, an ethyl group, alcohol, and methoxy. The dienophile is going to be this. Remember, you need an alkyne because you need to end up with a double bond at the end. So on this one, we're going to get alcohol, this, OME, and we're going to get that for the dienophile. So this, so then the question asks which one is better to use to make this product. This is electron donating. This is also electron donating. So we got 4 electron donating groups in the diene, electron withdrawing group, and 2 electron withdrawing groups. So this is set up perfectly to do a Diels-Alder. This over here, of course, these 2 are still electron withdrawing groups. These are split, so this is the better one. All right, that's the last page on this worksheet. So that's it for this week.